hello everyone. Good morning and welcome to the session. And yes, thanks for joining me. So let's start with the regular business. And the topic that we are discussing about is we are talking about wave. So that is what we had done last time, and we were talking about other situations like how can the speed of wave be related to different thing and all those stuffs we were discussing. Let me just check. All right, so now let's see. To consider, say, last time we had discussed one very important thing, and that is something like this. If you have a wave, the wave have three parameters. One is the wave speed, the other is the wave frequency, and the next is the wavelength. So these are the three parameters which characterizes a wave. One is wave speed, other is wave frequency, and third is the wavelength. We had discussed this thing in a smarter way, that when it comes to wave speed, then wave speed depends only on, so the wave speed depends on medium. So if you change the medium, the value of wave speed will change. But one should not carry a misconception that wave speed depends on wavelength and frequency. No, it does not. Wave speed depends only on the medium, the characteristic. It could be the wavelength, it could be the density, modulus of elasticity, any characteristic associated with the medium. That is where the speed will depend. The frequency, that depends on source. So you have two different sources. Like typically in case of sound, the sources that we have is like a tuning fork. So you have two different tuning forks. The frequency of the sound produced will be different. And finally, the wavelength. The wavelength is V into V by frequency, the speed divided by frequency. So wavelength is an something you should say is not an independent thing. It is a parameter which combines both speed as well as frequency. Or you may think in this way, the speed of the wave and frequency of the wave is related by a factor, and that factor is called as the wavelength. So this is how we understand about the speed, frequency and wavelength. Now let's go step by step. The first case is if we talk about the speed of, or let's say the transverse wave in string. Now I'm talking about a thin string, and if you have a string, then a string can support only transverse wave, and we would like to know what would be the speed of this transverse wave. And we have a formula. After doing all those things, you get the speed of a wave is under root of t divided by mu. The speed of a wave comes root of tension divided by mass per unit length. So this t is the tension, and this mu is the mass per unit length, or it's also called as the linear density. So you may call whatever you wish. T is the tension, mu is the linear density. Now depending upon situation to situation where the value of tension varies, we see that the speed of wave also varies. Like say for example, one simple question, if someone gives you, just to quote a very simple one, and you know majority of the question comes of the same pattern. Like let's say this is 4 kg and this is 1 gram and this is 1 meter. So the length is 1 gram, length is 1 meter, the mass is 1 gram, and the mass which is hanging, that is 4 kg. And I would like to calculate the speed of the wave in the string. Please give a try. How would you go to calculate the speed of a wave in a string under this condition? So the speed of the wave under this given condition would be equals to under root of tension. The tension is provided by this load, and tension has to be kept in Newton, so that is 40 G, keeping it as 10, divided by mass per unit length. Now you see the mass of this particle is 10 raised to the power minus 3 and length is 1 meter. So we have just fit the value of tension and we have just done the mass per unit length. This is mass per unit length. So 10 raised to the power 4, in other words, that will be 200 meter per second will be the speed of the transverse wave, the speed of the transverse wave when it reaches or when it travels in this thing. All right, so this is how we calculate the speed of the wave. That's great. Now, another important aspect of, the wave in this string is, there's one very beautiful point, and try to understand. Let's try to understand the energy of a wave. So you want to understand what is the energy of a transverse wave. Great. So people have come up with answer like Siva, Divyanshi, Kaval Singh, Shruti, Shri Krishna, Vathika, Divya, Kanika, Rajvardhan, Shaurya Mitra, Ashita, Ashutosh. Great. Keep it up. Keep it up. Kotis, that's great. So this is, now I would like to talk about the energy of a wave in a string. And you should understand, when it comes to energy of a wave, that is summation of kinetic energy plus potential energy. So that is the energy of a wave in a string. Now just understand, what is kinetic energy? If you see, the kinetic energy is the kinetic energy of particles oscillation. This is the kinetic energy of particles oscillation, which goes up and down. At the mean position, the kinetic energy would be maximum. At the extreme, the kinetic energy would be 0. So that's a regular affair. What about potential energy? Now this is a point where people be a bit confused. The type of potential energy that we are talking about, so we have different types of potential energy. It could be electrostatic, it could be gravitational, it could be elastic and all. And the potential energy associated with a stretched string is in fact the elastic potential energy. So elastic potential energy, that means that is related to 1/2 of stress multiplied by strain multiplied by volume. So this is that potential energy of a wave in a string. Now with this thought, you would get a very nice consequence, and let me show what it is. Say, imagine a string is there, and once a wave passes through the string, the shape of the string will change. So at any given instant, the shape of the string will be something like this. I have over amplified the figure. It's not that, like if you see a typical string where the wave is propagating, you don't find such sort of big wave. Like this is the string, and you can't see those crest and trough like the ocean waves. You can't do that. That's very small. I've already said I've over magnified the view. Now just say, initially the length of the string was this, and now the length of the string has become this. Since the length of the string has increased, the energy stored in the string would also increase, and that's in the form of elastic energy. Now let's come here. Just think very interestingly, this length of the string, this particular length, now has become this much, and you could see there is no change for this length of the string. What I want to do is that I want to see what is the individual components' participation in terms of kinetic energy and potential energy. So I just want to see the individual component, And you could say the first component is this. And this small component has this much of length. And you could say for this, the kinetic energy is 0. Why? Because it is at the extreme position. At the extreme position, the speed is 0. But for this, the potential energy is also 0. For this, the value of potential energy is also 0. Why? Because the elongation suffered by this particular length segment is 0. So that may surprise you that kinetic is 0. That is very simple. But we are used to thinking in this way, that if kinetic is minimum, potential should be maximum. I'll justify that. Keep that part, hold on. But right now just see the elongation of that segment is 0, you can understand. Now another interesting thing, talk about this segment of the particle which was initially here. Now this segment has reached here, so that segment has become this much. So imagine a horizontal segment here, its length has increased and has become equal to this much, and it's a clear indication that there is the maximum elongation of this segment. And if the elongation is maximum, obviously the potential energy will be maximum, but this is also at the mean, so kinetic energy is also maximum. So this fact kinds of a bit confuses students, so be careful that the particle at the mean while the wave travels, both the kinetic energy and potential energy are maximum. Now requires the justification, why isn't it happening that when kinetic energy is 0, potential energy is 0, or potential energy should be maximum, why isn't it happening? The answer is, if you expect that when kinetic energy is minimum, potential energy is maximum, and vice versa, you can expect this, but that happens only in a closed system where no energy exchange from surrounding to system or vice versa happens. So to make it in a simple word, no energy exchange means there is no external source which is continuously imparting energy to this system. When those sort of closed systems are there, obvious the kinetic mean will give maximum potential. But in case of wave, there is an agent who is constantly oscillating the string. There is an agent who is constantly imparting the energy. So in that case, we cannot expect that when kinetic is minimum, potential would be maximum, and vice versa. Alright, so that was just a small thing that you need to understand. Now let's come to the case of waves in general medium. I'm talking about the longitudinal wave. So if you see about a longitudinal wave, now longitudinal wave is there in solid, liquid as well as gas, and we would directly say that if you have to see the longitudinal wave, velocity is under root of E divided by rho, where E is the modulus of elasticity and rho is the density of the medium. So that is how the speed of a longitudinal wave depends upon the medium. And then you would see one thing, the value of modulus of elasticity depends on what sort of medium are you choosing. Like if I directly focus my attention to air or gas, so speed of sound in gas would be under root of B by rho, where B is the bulk modulus, rho is the density of the medium. So in that given case, this comes out to be the speed of gas, because the only modulus of elasticity which is defined for gas is B. But you know, the gas is process dependent. For different processes, the speed or the bulk modulus would vary, and the propagation of sound is an adiabatic process, so that comes out to be gamma P by rho, and P by rho can be written as 3 RT by M. So this will be only RT by M. So this will be the speed of sound in gas. Please don't confuse as speed of gas. It's not speed of gas. it is speed of sound in gas is under root gamma RT by M. And based on this question, you get lots of modification, like what would be the speed of sound in hydrogen to oxygen, helium to nitrogen. So depending upon the value of molecular weight, the temperature in Kelvin, and gamma, the atomicity, you can calculate the speed of sound in the gas. Now there is one interesting thing, and that is very much important to understand, and this is talking about the intensity of a wave. This is very much important. So let's talk about the intensity of a wave, and let's understand what does that intensity of a wave have to do with. Let me make a space here, but basically you can start writing that intensity is power per unit area. So that's how we define intensity, and the unit of this intensity would be watt per meter square. The power per unit area, that's the intensity. Okay, now a very important thing, just try to see. Like if I talk about a point source, say I have a point source of light. So here is that point source of light, and that point source of light has a power P. Now it's very easy to imagine, if you have a point source, the wave spread, the wave distribution would be spherical in nature. So in that given condition, you would see it's always better to consider that the energy distribution in a spherical way. And let us try to see how much would be the intensity at a distance r. Well, the value of intensity here now is going to be I equals to P upon 4 pi r square, power per unit area. And why 4 pi r square? Obvious, because the distribution is spherical. And one more thing, guys, the same value of intensity can also be equated to 1/2 rho omega square A square multiplied by V. Even this thing can be done. That may surprise you, but for any wave, this is a new expression. If you haven't memorized it before, do it very carefully. That intensity of a wave can always be equated to 1/2 rho omega square A square V. Like velocity of a wave, it's something like this. If you try to understand, whether it is root T by mu, that can be equated to lambda F, whether it is root gamma P by rho, that can also be equated to lambda times F. Depending upon different types of media, you get different expression, but the wave speed can always be equated to wavelength multiplied by frequency. That can always be done. So the technique is same. Intensity is power per unit area, and any sort of intensity can be equated to 1/2 rho omega square A square V. What are the two important things that you get from this thing? The first important thing that you get is that intensity of a point source is inversely proportional to r square, because you could see from this two relationship. And next, as the wave travels in the forward direction, you should understand the wave would oscillate, or the particle would oscillate. So the oscillation amplitude here and oscillation amplitude here would vary. And let us see how much will that be. Like just concentrate on two particles. At two different points, density is same, omega is same, velocity is also same because the medium is same. So amplitude will vary. So now you can compare with this, that amplitude square is inversely proportional to r square, or amplitude is inversely proportional to r. So this is how we relate about the relationship of amplitude of wave with the radial distances. So that was the case for point source. Now let's consider the case for a line source. And if you want to have a view of the line source here, now let's not be so specific. For a line source, you know, the distribution is going to be in a cylindrical one, as against the point source where the distribution, the energy distribution area was a sphere. For the line source it has to be a cylinder. That's purely due to the symmetry of the figure. So you can come in this way, that intensity is P by 2 pi RL, power per unit area. And the same intensity can also be equated to 1 by 2 rho omega square A square multiplied by V, right? So this can be done. You could see here, that was what I was saying. Any wave you have, you can always equate the intensity to half rho omega square A square times V. And now just comparing these two relations, you get that intensity is inversely proportional to R. Likewise, you want to compare, then amplitude will be inversely proportional to root R. So those are the situation that you get for a line source. And after that, if I have another case, and that is for a plane source, that means just imagine a large source, not a point, not a line, but a large sheet of sound source. If you just assume there, by the proper geometry you could say that intensity would be constant, and if intensity is constant, the amplitude of the wave is also going to be constant. So this is the relationship of intensity of a wave as compared to different points of medium. There is another small topic in the wave, and that is quite important as regard to NEET examination, and that topic in case of wave is called as the sound level. Now let's try to understand what does that sound level mean. Basically, you have to understand that when you talk about sound level, say any intensity of a wave, the degree of loudness or slowness can always be measured, and it is measured in terms of sound level. Now what is that sound level? I'll show you. First of all, the I naught is 10 raised to the power minus 12 watt per meter square. Now what is this I naught? This is in fact the minimum detectable intensity. So this is the minimum detectable intensity. Of course, we are talking for human ear. So the minimum intensity that a human ear can detect is this much. And that's on an average value, 10 raised to the power minus 12 watt per meter square. That depends on person to person. Some may detect a very large, some may detect even a smaller one. So that's a debatable issue. So this is just an average one. Now we define for sound intensity I. Suppose if I have a sound intensity I, how much will be the sound level? That is log base 10 I divided by I naught. So this is how do we define the sound level for an intensity I. It's always divided by a constant I naught, and I is that intensity whose sound level you're interested to calculate. We'll see with a numerical, do not worry. And this is the unit, or this has a unit of Bell, named after Alexander Graham Bell. So this is how we say the sound level of a source corresponding to intensity I. Any intensity I whose intensity you want to find, you divide it by I naught and take the log, and that will be the case. But generally what happens is Bell is a very large unit, so people prefer to come in a smaller unit. Like if meter is very large, people would prefer to come in centimeter. Similarly, Bell is very large, so people would like to come one step smaller, and that is deci. So they call it as decibel. So this is what you get. That sound level is 10 log 10 into I by I naught decibel, and it will be having a symbol of small d, capital B. Small d because milli, centi, deci, kilo, everything will be written in small. So, and named after a scientist, so that will get the capital letter. Though in this sort of exam, you have no interest in this sort of thing, but still, it's always better to know this sort of convention. So, if I say that if I equals to 10 raised to the power minus 6 watt per meter square. Say I have a sound of intensity 10 raised to the power minus 6 watt per meter square. And I would like to know what is the corresponding sound level in decibel. So the idea would be sound level is 10 log 10. I is 10 raised to the power minus 6. Downstairs, it's always 10 raised to the power minus 12. This value would always be divided by a constant value. And this is 10 log 10, 10 raised to the power 6. For those who pretend to be weak in mathematics, it's not so weak. It's not so difficult. So the idea is, see, log base 10, 10 raised to the power 6 will be equals to 6. So this is 10 as it is multiplied by 6. And that's equals to 60 dB. So this is how we calculate the corresponding sound level. So a sound of intensity 10 raised to the power minus 6 watt per meter square will have a sound level intensity corresponding to 60 decibel. So that's a part all you people need to understand. All right, now after that, let's try to, yes, good Ratika, good Shubham. 60 decibel, very good. Now, after having learnt about the sound levels and all those things, it is time that we understand that what would happen if we add two different sound waves. What is going to happen? That is what we call as the wave superposition. So let us see what would happen in case of wave superposition. There are basically three types of superposition, and those three types of superpositions, let's try to understand. The first one is called as the standing wave, right? The first one is called as the standing wave. And let's try to see what is the condition required for standing wave. And the condition is this. You have A sine kx minus omega t plus A sine kx plus omega t. That's how it comes. This is the condition for standing wave. The two waves should be traveling in opposite direction, and the frequency and the wavelength both have to be same. I've seen a very unfortunate part that students know this superposition term by name. They know something which is called as standing wave, but they are not precise in the understanding that under what condition will you get standing wave and what the resultant would look like. So this is the idea. See, if you have two waves, then these two waves are traveling in opposite direction. So that opposite direction is very much of importance. You need to focus that. And k is same, omega is same. So that is the condition of standing wave. And if you get standing wave, the resultant amplitude will always be a function of position. So that is what we call as standing wave. So this is the chief characteristic about standing wave, that it is formed whenever two waves in opposite direction would be superimposing, and the outcome of a standing wave is the resultant will have a function of position. And there is another wave or the another pattern, and that is called as the beat. Now beat will happen when you get this A sine omega 1 t minus x by v plus A sine omega 2 t minus x by v. Now notice, in case of beat, there is something which differs. It's not the direction, it's the wavelength of the two, or the frequency of the two sources. But yes, omega 1 and omega 2 vary slightly. It is not that the variation is so large, the variation has to be very, very small. And why do people I naught won't be 10 raised to the power minus 11. No, Siva, it's 10 raised to the power minus 12. It's a standard value. And that's watt per meter you have written. That should be watt per meter square. All right. Okay, now let's come to this point. Omega 1 and omega 2 vary slightly. That is what we have seen. Now, why do we consider varying slightly? This is all for the reason, for all practical reason, because for the human ear to detect that beat pattern, the frequency difference should be small. I would not like to go because that will drag me to another territory where I don't want to go. And the third one, the third pattern of addition is called as the interference. And let's see, what is that interference about? If you see about interference, it is this: A sine kx minus omega t plus A sine kx minus omega t plus phi. Oh, by the way, one thing has remained here. When you add these two things, the resultant amplitude comes out to be a function of time. That's another great difference between standing wave pattern and beat pattern. And finally, in case of interference, this happens whenever you have wave of this nature and you get that the resultant amplitude, whatever you get, that is the function of phase difference between the two waves. So this is what you call as the interference. In interference, the direction is same, the frequency is same, but there is a phase difference, and you must have learnt it in very great detail in your class 12 that these sort of waves are also called as coherent waves. So that should not be a problem in understanding that. But the main part is that, see, you should have this thing in your fingertips: A net, function of position, function of time, and function of phase difference. That what is the condition to get a given structure and what is the outcome. All the things have to be very proper in your head. Now, in case of standing wave, some basic characteristic about the standing wave is that is something like this: that when you have standing wave, you have node, antinode, node, antinode, and node. So let me just slightly give a brush up of all this concept, that node, antinode, that's what you get. And the distance between a corresponding node and antinode is lambda by 4. Distance between node and antinode is lambda by 4. That means distance between a node and node, that comes out to be lambda by 2. And the characteristic of node is that the particle here is permanently at rest. So here the amplitude is 0, while here the amplitude is maximum. So at different position, the value of amplitude varies, and at node the amplitude is 0, while at antinode the amplitude is maximum. And the pattern of the standing wave which forms here, if you talk about the pattern here, this is node, antinode, node, antinode, and node. If you talk about that pattern, the pattern is something like this. Yes, so this is the pattern. The particle at antinode will have maximum amplitude. The particle at node will always be at rest at different instant. Like even if you see some instant, the shape of the string is something like this. So particle at node still has 0 velocity, the antinode is the amplitude max, node is 0. So that pattern keeps on going, but in any given case, the particle at node will always be permanently at rest. So there are patterns of the standing wave which comes, and one more interesting thing you should understand, that when it comes to a standing wave, all these particles are in same phase. The particles between two nodes are always in same phase. And what is the reason for that? Because you see, all are moving in the same sense. For example, if this particle is at its amplitude, this is also at its amplitude, this is also at its amplitude. So since all the particles are at their amplitude, the phase would be same. Similarly, the two adjacent particles will have opposite phase. Two adjacent should have opposite phase, because if one is at positive max, the other will be at negative max, or not only in max, even in any condition, they are always oppositely oriented. So this fact all you people should very properly realize. And then comes, say, different pattern of the wave, or the standing wave pattern comes. Out of that, I would be showing one, and you can get the idea. Like, say for example, if I have a closed organ pipe. In case of closed organ pipe, we go with this pattern, where you need to understand there is a strong question that can be formed. A regular question you can easily solve, but there are questions where you need to have a strong attention. Like, this is the organ pipe, and if I make the fundamental pattern of this standing wave which exists here, the fundamental pattern would be something like this. This is the fundamental pattern, where in the fundamental, this is the node and this is the antinode. Similarly, if you go one step ahead of that, if you go there, so the pattern you would be getting is something like this. This is what you get. So what is the difference that you can realize? Here, between this and this, the distance is lambda by 4. So you get L equals to lambda by 4. And here lambda by 2 plus lambda by 4, the value of L will be 3 lambda by 4. This is how it goes. Now you got to understand that at the fixed end, this is a node, but just remember, this is what I want to focus. This is the displacement node, because the displacement of this particle would be minimum, that is 0, that's a displacement node. While, remember, this is a pressure antinode. So this particular point, either you call it as displacement node, that's fine, or you can also call it as pressure antinode. Though I haven't derived it, it's not possible, but you need to understand this fact as a very important property, that displacement and pressure, they have a phase difference of pi by 2. Remember, the displacement wave and the pressure wave have a phase difference of pi by 2. Wherever the displacement is maximum, the pressure is minimum, and vice versa. So the point which is a displacement node will be a pressure antinode. Likewise, if you talk about this point, this is the point here. This is the free end. So this particular free end is the case of displacement antinode, and this is itself the pressure node. So pay attention to this. A point which is of displacement node would be a pressure antinode, and vice versa. So that's a point you need to understand. All right, now let's talk about the pattern or beat that forms, and let's try to understand it. In case of beat, the condition of beat that forms here is It is formed when two waves of slightly different frequencies are added. So when it comes to beat formation happens whenever two waves simultaneously play and they differ in frequency slightly. So if one has a frequency f1, other has a frequency f2, let me just list up the values which are probable. We will not go into the derivation. The frequency of the wave will be f1 plus f2 by 2. The frequency of the amplitude is f1 minus f2 by 2 mod, whichever is bigger, you can go with that. And the frequency of the intensity of wave is mod of f1 minus f2. A very important data. The relationship between f1, f2 and different frequency. Like the first one we said frequency of wave, frequency of amplitude, frequency of intensity. And guys, you got to remember one thing. This frequency of intensity is itself called as the beat frequency. So the meaning of beat frequency is the frequency of intensity. But what does that signify? Let me try to show it. I'll just show it with the help of a picture. In fact, remember one thing. How does beat appear like? How does it sound like? Let's try to say. It's something like if you play two sound together, one is a constant sound, the intensity does not go up, does not go down, flat, constant. It is also flat. But when you play these two flat sounds together, sound would go up and down, and this is quite miraculous and very unimaginable. That there is one sound which is flat, another sound which is flat, but they differ in frequency, and when you play those two sounds together, miraculously, wonderfully, you get the sound would go up and down, up and down, up and down, and that pattern is called as the beat. So how would a typical beat wave, if you add two sounds, how would the intensity of the resultant vary like? It's something like this. Like two waves, they are individually, now this is very interesting, individually they are of flat intensity. When you play up together, goes up, goes down, and guys, this is called as the beat frequency. Actually the beat frequency is here. So this is called as the beat frequency, and that is the number of maxima heard per unit time. Number of maxima heard per unit time, that is called as the beat frequency. So numerically, as I said, the beat frequency is this, and in terms of the wave diagram, in terms of waveform, you get this. Let's see, some good questions and good tricky questions are always there in beat. So let's try to see, let's try to beat the beat. The first one is, say, the basic point is we will be focusing on this, that people would give you two frequencies and people would ask find the beat frequency. So here's the question. F1 is 100 and F beat is 5. So please calculate the value of F2. Please do that. There are two sound waves. One is 100, other is 5. You need to calculate the second frequency. Please do that. Options from many people, and that's very good. But the correct one that I've got is from Shaurya Mitra. That's 105 or 95. Next is Radhika, and next is Kaval Singh and Seema Nazneen. So if you say 95 Hz, that means it's not incorrect, but it is incomplete. Shavani Roy comes with 105 or 95. So far, whatever options I got. So this is what. Let's see how it comes. And it's quite simple. No big rocket science. one frequency is 100, the beat frequency is 5. So you need to calculate F2. There are two possibilities. Either you say F2 minus 100 equals to 5, or you say 100 minus F2 equals to 5. Because beat frequency is the difference in two frequencies. And we do not know. We actually don't know whether F2 is greater or F2 is less. We don't know that. So therefore you need to take both the possibilities. According to this, F2 will be 105. According to this, F2 will be 95. So both 105 and 95 is going to produce a beat of 5 while played with 100 Hz. So that thing has to be clear. So Janvi, Kotesh have additionally filled up with the option. That's great. Now let me add one more question. For that we need to see the point. There is one thing which is called as, suppose if you have a tuning fork, basically a question related to tuning fork of frequency in this wave, in this topic of beat. So let's see what is that. In case of tuning fork, just remember this thing, that you are not supposed to read the entire detailings of tuning fork, but there is a process called as filing. So for a tuning fork, as I said, we're talking purely for a tuning fork. If you file a tuning fork, so file means rubbing, like with a sandpaper you do it, or with a nail filer you do it. So filing means you are thinning, you're slimming the tuning fork. So filing, in fact, increases the frequency of a tuning fork. And there is another process which is called as waxing or loading. So when you wax or load a tuning fork, the inertia of the fork increases, it gets heavier. So if it gets heavier, then oscillating frequency will decrease. So that decreases the frequency. It's a very important fact that if it comes to a tuning fork, these are the parameters that you need to be ultra careful with. That what does filing have an influence in its frequency? What does waxing has the influence in its frequency? So now let's see a question related to this. Like in the previous question, you could not figure out exactly whether it is 105 or 95. You could not do that. You could say that either of 105 or 95 was the frequency. But now we'll put a question and we will add one more condition in the question. And with that one more condition, you can exactly figure out whether it is 105 or 95. So let's see. It's something like this. F1 is 100 Hz. This is 100. And F beat is 5 Hz. So there are two tuning forks. One has a frequency 100 Hz. Other has a frequency 5 Hz. And it says that on filing 2, when you file 2, the same beat is heard. So when 2 is filed, same beat is heard. You need to calculate what is the original frequency of 2. Please do that. So F1 is 100 Hz, okay? F2 is 5 Hz. It's how it comes. So 105. Yes, please do. You need to calculate the original frequency of 2. That's great. Now good options are pouring in. That's great. Yes, so it is something like 95. Why? Let's see. The idea is, say, for those who could not follow, there are two options. Either F2 minus 100 is 5, that's the case. Either that's a situation, or sometimes you would get 100 minus F2 equals to 5. So these are the two situations you get. F2 minus 100 is 5, or 100 minus F2 is 5. Now you need to choose one among them. If this is true, F2 will be 105, and if this is true, F2 will be 95. Now how to make a choice? The question says when two frequencies increased, the difference is same. And let us see whether it's possible or not. It doesn't seem possible, because on increasing F2, the difference between them, because this is constant, on increasing 2, the difference between them further increases. So there is no way how you come back to the same difference. But this one, on increasing 2, you could see there is a possibility that the difference will exactly be same. Why? Because F2 increases and it becomes greater than 100, and the value also exactly satisfies, so that the difference will be 5 again. So there is a possibility for the second one, so it implies F2 is 95. Now, how do you get that? You just try to understand. 100 with 95 will have a beat of 5. 100 with 95 will have a beat of 5. Now what you do is that when 2 increases to 105, and 105 beat with 100 will back again be 5. So this is how we come up with the conclusion that the beat frequency is 5 Hz. So initially it was 95, you increase it and it becomes 105, and 105 beat with 100 will again be equals to 5 Hz. This is how it comes. There is another small discussion in beat, and that discussion is something like this. Like you have two strings and these are identical strings. Like these are completely identical strings. One has tension T, other has tension T, and they are having a frequency F. If the strings are completely identical, then the frequency produced would also be same. Now suppose by any means I change the tension in the string, either in the first string or in the second string. Like say I increase the tension in the first, or I decrease the tension in the first, anything I do, then there will be a mismatch in frequency, and that mismatch in frequency itself is the beat frequency, because beat frequency basically is the difference. Now let me just try to show, like say for this, that tension is increased by delta T. So we've increased the tension in the string by delta T. So I get, F equals to 1 by 2L root T by mu. I'm assuming that you know this, the frequency of a wave pattern in case of string, the standing wave pattern. If not, you need to check seriously about your preparation level, because this is a very simple question. Now say that L is constant, mu is constant. So delta F by F will be 1 by 2 delta T by 2. Think about the error analysis way, that delta F by F comes out to be half delta T by T, and that delta F is 1 by 2 delta T by T multiplied by F. And realize delta F is the increase in frequency of this if tension is increased by delta T. But then if you cleverly realize, the increase in frequency itself is the frequency mismatch, because this frequency is still F and this increases by delta F. So the difference is delta F, or as I said, the mismatch in frequency is delta F. So this itself will be the beat frequency. Okay. Now this was about the ideas of beat. Now we'll go to the next topic in case of wave, and that is the Doppler's effect, and that is one of the quite important portion from which you get lot varieties of question. So let's see that. All right, so now let's see what is that Doppler's effect all about. Actually, you know that whenever the separation between the source and detector changes, there is always an apparent frequency which is observed or which is detected, and that is what you call as the Dopplers. Now, to get straightway to Doppler's effect and its business, you can straightway see that F apparent is F V plus minus Vd by V plus minus Vs, where V is the speed of sound, right? This V is the speed of sound, and this Vd is the speed of detector, Vs is the speed of source. Please don't confuse, Vs is not the speed of sound, Vs is the speed of source. So this is the underlying formula which will help you to compute apparent frequency. But remember one thing, you need to understand one very important point. How to confirm that which sign is positive and which is negative. And the idea is very simple. I would say instead of going through sign convention, you just go with one simple way. And that is, see, the detector has a control in numerator. So if due to detector the frequency increases, and you know when does the frequency increase? When the separation decreases. So if due to detector the frequency is increasing, upstairs will be plus. And if due to detector frequency decreases, this would be minus. In the similar way, the control of source is in the denominator. And if due to source the frequency decreases, then downstairs will be plus. And due to source the frequency increases, then downstairs would be minus. So this is how we come up with the conclusion. Examples will make everything clear. So the first thing is, say, imagine this is a source and here is the detector. And what you do is that, let's say the detector is at rest and the source moves with a speed u towards the detector. Please calculate the apparent frequency heard by the detector. Please do that. All right, so let's see how it goes. To calculate that apparent frequency, yes, I get it from Satyam, Sri Krishna, Ashutosh. So Ashutosh is right, Sri Krishna, that's right. Siva, Sandeep, you made a slight mistake in the sign. Shashi, she's right. Yes, Kamal Singh, you're right. Rathika, she's right. Shruti, perfect. So it goes in this way. Now let me show for other people. Let me call that apparent frequency as F apparent. Now say detector is at rest, so upstairs will be V. The source is moving, and due to the source the frequency increases. So to increase the frequency, of course denominator would be subtracted, so that's V minus U, and that's all. So go very, very light-headed that the control of source is in the denominator, so you can go in that given way. Okay, now another case. Please go with this. The source is at rest and detector is moving towards the source with a speed u. Please calculate the apparent frequency. Please do that. Good, Divyanshi, good. Yes, guys, so here you get, as the detector approaches the source, you get F apparent is F V plus U divided by V. That's what you get. F apparent is V plus U divided by V. That is what you get. And now you could say one thing. Okay, how did I get? Let me show. For those people, because this time the detector is moving, the source is at rest, so downstairs would be only V because source is in the denominator. Let's see the upstairs. Due to the action of detector, the frequency is rising because the separation is decreasing. So upstairs has to be plus V plus U, and that's how you get this. And you get one very interesting thing, that if I call this as F apparent dash, F apparent is not equal to F apparent dash. And if F apparent is not equal to F apparent dash, it really means there's a whole lot of difference in saying that the source is moving or the detector is moving. There's a big difference in that. Though the speed was same, but you could see the apparent frequency detected is different. So in that case we say that Doppler's effect is unsymmetrical. So Doppler's effect is not symmetrical. Had it been symmetrical, then both the situations would have yielded same answer. Source towards detector or detector towards source, both would be same thing. Now next let's try to see. But there is a certain condition. Just try to see F apparent, I'll bring the same one, F apparent, that is equal to F of V. I'm continuing the same one by V 1 minus U by V. I'm putting certain condition, I'm making certain bargains, and this V and V gets cancelled. So F apparent is F 1 minus U by V raised to the power minus 1. And just realize that U is the speed of detector source and V is the speed of sound. And you know, the speed of, in our day-to-day life, in the life where we live, the speed is very, very less as compared to speed of sound. So if I say this is equal to F into 1 minus minus 1 U by V, what I have done is that I have used the binomial expansion, that 1 plus x raised to the power n would be 1 plus nx, and that comes out to be F 1 plus U by V. Of course, I'll put the condition that when U is very, very less than V, that's the case. And this frequency exactly matches to F apparent dash. So from this conclusion, what you can say is that, yes, agreed that Doppler's effect is very unsymmetrical, that's fine. But if U is very, very less than V, if the speed of object, if the speed of source or speed of detector is very, very less, so in that given case, F apparent will be equals to F apparent dash. That means Doppler's effect in that case would be symmetrical. So just be careful with this thing, that under special condition, and the condition is this, speed of either the source or detector is very, very less as compared to speed of sound, Doppler's effect would purely be symmetrical in that situation. Let's move further. Let's try to see. See guys, there is another case, and that is something like this. I'll just show you one thing, like a detector is there and a source moves in this direction with a speed u. After some time, as the source crosses, the source reaches there, and that means that's how it goes. Starting from here, it finally reaches there. And we would like to see that how does the frequency observed by the detector change. Let's try to see. initially, let's say, initially means when the source is towards the left of the detector. That's going to be F1 is F V by V minus of U. That's how it comes. And just try to see, why did we write this? Because the source approaches towards the detector, so the frequency increases. That's how it goes. And finally, when the source reaches this side, the frequency detected F2 will be F into V by V plus U. That's how it goes. So one is the initial situation, other is the final situation. And if you want to calculate, say, how much would be the beat detected? Yes, you've heard it right. Back again to beat. Any question in sound wave can be linked to the concept of beat. Whenever you have two frequencies associated, people very gently put the question that how much is the beat? And that beat is the difference in two frequency. It's very simple. F1 is greater, so that will be F1 minus of F2. And let's say that is how much? F of V by V minus U minus V by V plus U. That's how it comes. And let's see, FV, this is how it comes. V plus U this much, so 2U divided by V square minus U square. So that is the beat frequency which is detected by the detector. So as I've said that, whenever people get the opportunity, people would always put that question of calculating beat frequency. And one thing, say, like learn the art of approximation. If U is very, very much less than V, this U is subtracted, so this can be neglected. So you get F beat equals to 2V U into F divided by V square. So this is 2U by V multiplied by F. So that will be the beat frequency if you really want to, reduce it by the application of Bernoulli's the binomial expression or the limitation. Now after this, let's go to the next point, and that is whenever this is source and this is detector and the source moves with a speed u, say, now the motion of source is not along the line of sight. So essentially say this angle is theta. So in that case, the component of the speed towards the line of sight is u cos theta. So everything would be same. The only point is that you need to calculate the component of the speed along the line joining them, and that is u cos theta. So the effective speed for frequency decrement is u cos theta now. And you get F apparent is F of V by V minus u cos theta. This is only the difference you get. This is only the difference you get because u cos theta is in this direction. That's the speed of source. And continuing with the same thing, you would get this thing. Like here, if the detector is at center and the source is moving, the angle is 90 degree. F apparent would be equals to real frequency. You just need to put theta as 90 degree. You get F apparent equals to F real. All right, people, so this much I would be allotting for the waves. I've figured out the most important thing and I've just made the focus on that. Now let's move to the second year syllabus, the class 12 syllabus, to begin with the electrostatics part. And in electrostatic part, the computation of force and all, we're not going to talk about that directly. Let's talk about the electric field. So let's see how are we going to understand the pattern. All of you know the value of electric field is kq by r square. That's electric field due to a point charge. And if it's a positive charge, field is away. If it's a negative charge, the field is towards. That's how we come. Now there's a first question that you need to calculate, and that is something like this. This is say 4q and this is minus q. Separation between them is A. Now positive charge will have electric field away, negative charge will have a field towards. You need to calculate the null point. So what would be the meaning of null point? The point where electric field will be equals to 0. Give a try, please do. So I got answer from Sashi Pritham, 3a by 2, but I would like to know 3a by 2 from where? Can you please explain octave? Yes, certainly. Kanika, I'll explain. Let me just do it and I'll just explain to you octave. So it's something like this, say. Say the null point is the point where electric field will be 0. First of all, this zone cannot have null point. It cannot have, because 4q will give a field away, minus q will give a field towards. The direction is same, so cancellation cannot happen. This point cannot have null point, although the directions vary. 4q gives the field away, minus q gives the field towards, but the magnitude of the field can't be same, because you're closer to 4q, so magnitude can't be same. So the only area where you have null point would be here. Let's say this distance to be x. That is a plus x from 4q and x from minus q, so that the direction is opposite and the magnitude would also be equal, because that's closer to the smaller charge. So now the calculation of null point will be k4q divided by a plus x whole square is kq by x square. So 2x, if you just say, is a plus x, so I get the value of x as a. So the null point will be 2a from minus of q. That's how it comes. I don't know why all the people have come up with 3a by 2. Let me just say, why could have 3a by 2 come? I got the thing that you made the mistake. It's not 3a by 2 from negative charge, it's a. What all you people did was that even while equating the magnitude, you wrote the negative sign. That's not allowed. This is equating the magnitude. So when you equate the magnitude, you cannot write the negative sign. So that will be a from q. Now let's see how many would be there for a from this. Let's see. None so far. X equals to 2a from minus q. No, it's a from minus q. Yes, Ashmit, I'll do that. Ashmit, sorry. Ashmit, first of all, null point is the point where electric field is 0, net field. So first you need to search by hit and trial. This is 4q and this is minus q. So how would the electric field be 0, Ashmit? The magnitude has to be same and the direction has to be opposite. So Ashmit, this point cannot have null point because 4q will have away, minus q will have towards. The direction of the field does not fight, so there can't be null point. Here the direction of the field fights, 4q away, minus q towards. But though the directions is opposite, magnitude can't be same, because closer to 4q and farther from minus q, the magnitude can't be equal. So the only option that you have is somewhere here, closer to minus q, so that here the direction fights 4q away, minus q towards, and the magnitude would also be equal. So now let's try to see how are you going to calculate that. Due to minus q, that's kq by x square, which majority of you did the mistake of writing negative sign. You can't do that. It's equating the magnitude. And for this is k 4q by a plus x whole square. So you get the value of x as a. So Ashmit, hope I've made it clear for you. So x equals to a from q. So Vinayak has come up with the correct answer. 2a from 4q, Parth, Ashita, that's great. A from minus q, Shivani Roy, that's great. Shri Krishna, that's great. Ashmit, this must have been clear to you, right? Now, Kanika wanted to know about octave. So let me discuss Kanika. She wants to know about octave. So this is a concept related to sound wave, and basically the octave does not mean 8 times. Remember that. Octave doesn't mean 8 times. Octave basically means twice. That's octave. So it's something like this, say. I'll just show you. If F2 is n octave higher than F1, so you get F2 is 2 raised to the power n times F1. That's a meaning. If F2 is n octave higher than F1, F2 will be 2 raised to the power n F1. So if F2 is 1 octave higher, F2 will be 2F1. If F2 is 3 octave higher, F2 will be 2 cube of F1. That will be 8F1. So that's how it goes. Kanika, is that clear? Thank you, Ashmit. Thanks for the confirmation. All right, so this is how we start with the concept. You could see you must not be at all confused with the concept of the null point. Now just tell me, I'll give you another configuration and you just try to find out. Thank you, Kanika. Thanks for the confirmation. Now let's say this is Q, this is minus Q, a dipole, separation is A. Please see where is the null point. Calculate. Where is the null point for Q and minus Q? Seismic wave Shiva Chidambaram is the wave of sound that is produced in the rocks. They are longitudinal wave. That is all that is required in your level. Seismic wave, when an earthquake goes, the wave that comes in the rock, that's called as the seismic waves. And there is a combination of transverse and longitudinal waves when it comes to seismic. So essentially that's the case, the wave in the rock. Brothers, sisters, there is no, you wrote A by 2, lot many people have come up with this. In fact, there is no null point. Null point does not exist here. Reason C, the null point can't be here. Why? Because the directions are same. Q gives away, minus Q gives towards. So since the direction of the field is same, the null point can't be, yes, Sri Krishna, that's great. Null point, I mean here the field can't cancel. Here it can't cancel, though the directions are opposite, but minus Q and Q, closer to minus Q and farther from Q, the magnitude can't be equal. So since the magnitude can't be equal, so electric field can't be 0. So here the direction is same, no question of cancelling. The direction is opposite, but the magnitude can never equate. So got to be very careful. So I've got Siva, Ashmit, Kotesh, Sri Krishna and Shreya Bhardwaj saying no null point. That's all. So people, let me sign off from today's class. Thanks for being with me. Thank you very much. See you tomorrow.